Hey guys, we've been talking about Manual J, which is a term that describes HVAC calculations. And right now, I'm going to introduce you to who I study with. So, as background, if you want to learn more about this on the level 101, you should go and watch Matt Reisinger's video about this topic. I went onto his channel and talked about this for about 40 minutes and give you a tour of Manual J report. And people like me go to train to level up. And this is the guy that I go to train with, Alex Meany. Alex, thank you very much for being here.
It is my pleasure, sir. Thank you.
So before we continue and you start to wow people with your wizardry, will you please let people know how they can follow you?
So right now the social accounts are mostly focused on Facebook. I will probably have something eventually on Twitter that says Mean HVAC, but if you want to follow me, come to my website, meanhvac.com. Really easy. Mean, like you big mean person, HVAC.com.
Not really. He's a cuddly teddy bear, but
last name.
And I love that he's too cool for social media. So we're going to put him on our channel. So this is where they're going to make a big nerdy video out of this.
Yeah.
So thank you for making the trip because I think that person's going to be cool. So what I'd like to do first is Manual J calculations. I hand off Manual J reports to people all over the country for their projects, and I try not to have them piss off their HVAC installer with it.
Good luck.
But one of the things that's in there, if you print out the full report, which I'm trying to give people a 20, 40-page report if possible, for the HVAC guys who are doing this, please just show your work. That's all we're asking. When I give them a full report, there's a page in there that says, here are the duct sizes that you should use, and here are the CFM that are required for each room. Can you dig into that a little bit?
Yeah. In order to do a Manual J calculation, you have to estimate the duct load, okay? If you're going to estimate the duct load, you have to know something about the surface area. If you're going to guess at the surface area, you got to figure out how much air is in the thing. So in order to make Manual J go, they have to make here's a key word, guess at how much air is going to be in that duct system to make that Manual J calculation work right.
Pause for 1 second.
Absolutely.
A lot of my kind of clients are doing encapsulated conditioned attics. And I actually have zero duct load on probably about 75% of the loads that I run. But it still shows
that's
up.
why the mechanism is there.
Okay, so it's still there when you...
Yeah, the math is in there, and they built it in there so that because you needed to make a guess in order to make that happen.
Understood.
But the key word here is estimated, right? And estimated is another word for, ballpark, made up, rule of thumb, whatever. And it's not necessarily going to be what my target airflow is, because one of the more annoying things I'm very fond of saying is Manual J does not tell you what equipment you need. Manual J doesn't tell you anything about the equipment. It tells you about the building, right? It tells you how much heat you gain. It tells you how much heat you lose. It tells you how much moisture you gain. That's all it does. Then your job is to go find a piece of equipment that will make that happen, right? It'll replace that heat. It will remove that heat. It will remove that moisture. So when you're doing a Manual J, all that report is coming. If you haven't decided what your equipment is, you don't know what your airflow needs to be, because when they engineer those systems, they engineer them differently, right? Once upon a time, everything was 400 CFM per ton. Now everything's 350 CFM per ton. Well, there was a transition there where who knew how many CFM per ton it was, right? So when you're looking at a Manual J report, don't size off of Manual J until you've decided what your equipment is. Now, if you've decided what your equipment is, you can enter the CFM amount that you need. Now, that's Manual S. I'm getting ahead of ourselves here. But if you've entered that, yep. And if you do enter that, now those CFM numbers are going to be accurate, right? Those are going to be your target CFM numbers. But if you haven't decided on your equipment, it's all based on an estimate. And I know the formula. I'm not going to bore you guys with the formula, but it is based on a very big guess about the delta T across the coil, about the temperature difference across the coil. I don't know what the temperature difference across the coil is. I haven't even picked the equipment out, right? That's a thing you have to use equipment in the field to test, but it makes a guess based on how much sensible and how much latent you have. So if you're in a very dry climate, it will throw really high numbers at you that you might not want to end up using. And if you're in a very humid climate, it might throw some surprisingly low numbers at you because you have a very low sensible heat ratio. But and it makes sense, the physics checks out, but it's still a pretty big fat guess for something where the technology is changing really fast in the industry.
I want to make sure that everybody's clear that the report that you're going to get when you get a Manual J is going to say a tonnage that's recommended. like 7 tons or 40 tons, which I saw recently,
Oh, that's
or
good.
more like 2 for a home that's going to be a high performance home. And so that number doesn't actually mean anything because you use the manual S to do the next part. Now, the other thing is that when somebody like me in Atlanta does a load calc for somebody in Hawaii, for example,
Sure.
the guy who is actually in charge of installing that system is going to be pissed off probably that some guy who's halfway across the world
Might be.
did a calculation for him. So this next step of picking the equipment, you don't want to just do and then say, here's what I want you to use, because
That's fair. That's fair. When I'm doing third-party design, if I'm working with a builder, I try. And by the way, I don't want to do your designs. I want to teach you how to do designs. That's what I prefer to do. Occasionally, I get bored and somebody wants my help, and I'll do a design. And when I do that, I always want to get the HVAC contractor involved, right? Okay, great. Builder's my customer. Who's your contractor? Because we got to talk about the equipment that we're going to use here. I got to make some choices. And if they don't have any input on those choices, there's going to be friction right off the bat. So it is a very good idea to get on the same page equipment wise. Absolutely. And it's really important. I know I said it already, but it's really important to create the distinction of the manual J. And okay, I'm going to be a nerd here for a second. Manual J, J is for joule, all right? And joule is a unit of heat, right?
no way. That's great.
Yes, the
Thank you
manual,
for
yeah,
teaching me
manual
something.
J it stands for joule. That's where they came up with manual J. It's load, right? How much heat comes in, how much moisture comes in, how much heat comes out. That's it. Manual S is for selection, actually, and it's for choosing the equipment. And when it comes out with 2.1 tons as an estimate, not a bad estimate, but as an estimate, that does not mean you round up to 2.5, right? It means there's probably a 2-ton that will do it, but you better pay attention because it's a little on the high side and it's possible to pick something that might be undersized in that 2-ton range, right? Those estimates are generally good in most climates. One of the things you're going to find is in very dry climates, they do tend to run a little high. Because the estimate is based on sensible load, and dry climates don't even have latent load. So this is kind of a built-in assumption that your system's going to do a little bit of both of those things.
Because that assumption is going to build in a 75% sensible, 25%.
It's whatever the software has as a default or the designer puts in there. But 70-30 is what RightSoft uses. I think Elite uses it.
Elite is 75-25.
75-25, okay. And it's all BS, right? When you pick the system, you actually have a lot of control over what the ratio is going to be from sensible to latent. And what a lot of people confuse is the ratio of sensible to latent of your load and the ratio of sensible to latent of your equipment. Just because your building needs 20% latent doesn't mean it's going to get it. Right? You got to pick a piece of equipment for that can do 20% latent. You could undersize that. You can't really oversize latent, but you could oversize the sensible. You have to look at what the system actually does and match those things up.
Nerd level 5 question.
Okay.
Which is a digression. I'm sorry. We're going to get back to this, but the design temperature is the maximum temperature, not maximum,
Yeah,
100%, whatever.
it's
But the
1%,
design humidity, I've been told by humidity experts, is not at the design temperature.
Absolutely not, which is even worse because now your air conditioner isn't running because it's a cooler day, right? The humid days don't happen on the hottest days, right? So actually, if you want to find out more about this, there's a website that I highly recommend. It's put on by a volunteer group, and it's fed by information from ASHRAE. It's a pretty technical tool. It's a map of the world, and you find your place on the map, and you right-click somewhere on the map, and it will bring up a scary amount of data. Right now, if you're here in the U.S., you're going to want to set the thing to IP. That's imperial units. Otherwise, the numbers aren't going to make a lick of sense because they're all going to be in Celsius. But when you look at that 1% day, that's on your cooling day, the numbers that you're looking at are the 1% dry bulb. So they focus on the dry bulb. We take all the hours of this dry bulb temperature, 1% of them are warmer than this. Here's our magic number. And then the number that goes with that is the mean coincidental wet bulb, right? And it's the mean coincidental wet bulb because this is typically what the wet bulb is when it's here. So it's literally the opposite. It's at those temperatures, this is what the humidity level is. But if you look in the next section down, it says dehumidification. And you will see a dew point, because that's a very good way to measure the actual amount of moisture in the air. Wet bulb's kind of a weird way to do it, but it's because it's relative to your dry bulb temperature. They're measuring it. They use the mean coincidental wet bulb. But when you talk about the dehumidification day, you look at the dew point and the mean coincidental dry bulb, right? And in some climates, that dew point is going to be way higher than the dew point of your design day, right? And in some of those same climates, the outdoor temperature will be extremely low compared to your outdoor dry bulb day. One of the things you can do with the load calculation tool, I don't care what tool it is, there's places where you can change those outdoor temperatures. Now, you're not supposed to do that if you're, we're getting into a little, you got to be careful. You're not supposed to do that. But if you're going to find out what happens on the peak dew point day, you can plug those numbers in. Right? There's no crime in finding out what happens, right?
So technically, for those of you who are running manual J's, this is a save as, and you save it as dehumidification, right? Okay.
And I just have this piece of information over here so I can quantify what's going to happen on the worst day of the year, right? Not the worst day of the year temperature-wise, the worst day of the year humidity-wise, which we know for indoor air quality and for comfort can be a lot worse, right? These shoulder seasons are murder. So if I wanted to know what the situation was there, I could use those data points. By the way, they do recommend using the 1% for that as well. There is a 0.4 and a 1 and a 2. They usually go with the 1%. There are some experts who recommend 2, but the consensus seems to be to use the 1%. So you can find out what that is, and man, it will knock your socks off because your latent load is going to go way up and your sensible load is going to go way down, and you're going to look at what your equipment performance is, and you're going to go, uh-oh.
Need a dehumidifier.
Yeah. Very likely, yes. And some climates are worse than others. And another reason I like it is dew point is a very good number to consider when you're considering the scale of the problem, right? One of my favorite things to talk about is you don't want to design a system for 68 degrees. I don't care what your homeowner says. I don't care what they think they're comfortable at. Homeowners have no idea the temperature they're comfortable at, to be honest with you, because homeowners typically haven't lived in a house that had a properly designed HVAC system. Right?
True.
When somebody says, if you want to know my favorite trick for determining what indoor temperature I should design at, if you believe the homeowner should have input on this, do not ask them what temperature you want to keep the house in the summer. They will give you a dumb answer because they don't know about whether they're humid or whether they're hot. They just know they're uncomfortable.
No offense. There are homeowners watching this right now, and we're not talking about you.
Sorry.
It's everybody else.
I am. He's not. I am. So what the question I want to ask that homeowner is, what temperature do you keep the thermostat in the winter? That is a great question to ask. What temperature do you keep the thermostat in the summer? You're going to get insane answers. But if you ask them, what temperature do you want to keep the thermostat in the winter? You've removed humidity from the equation. Because I don't care where you are in the country. If it's winter, it's dry. So if it's dry, what temperature do you want to keep it is effectively what that question is. Right? And very few people will tell you 68 degrees, right? You might get a fat guy from Boston who tells you 65 and will throw this whole thing off, which, by the way, is where I'm at. And so this is where that dew point temperature comes in, because I don't keep my thermostat below 72 degrees in the Springfield, Massachusetts area where I'm at, because if I look at the outdoor dew point on a peak humidity day, guess where it is? Yeah, it's right around that point. And so now I've created a situation where anywhere indoor air and outdoor air meet, I'm going to get condensation, right? And where do you think those things meet? Do you think they meet in places I can see and know where they are? Or do you think they're happening in hidden places that I don't know about and over time are going to build up?
Stay tuned for Home Diagnosis Season 3 for pictures of that. So you need a dehumidifier, probably. Let's put a dog ear on that. Okay. Now let's talk about equipment selection, because that is the brunt of what Alex is getting at, which is how are we picking the actual piece of equipment that's going to do this?
Okay. So first, there's no such thing as a ton. Okay. Let that sink in. Sorry, HVAC people. Sorry, building science. Well, the building science people probably know it. Sorry, homeowners. There's no such thing as a ton. A ton is a nominal number. It's one of my favorite trick. I don't believe in asking trick questions of a group live without saying, this is a trick question, right? So I'll say, this is a trick question. How many BTUs are in a ton? And the brave people will say 12,000, because that's what they were taught. It's 286,000. What? Okay. So you're Willis Carrier. You're Dave Lennox. These are people who actually walked the earth, right? They created refrigerant-based air conditioning companies that were replacing ice melting systems. We had cooling in industrial systems. Thomas Edison's house in New Jersey had an ice melting system for keeping his home comfortable, right? We wanted to switch them over to this newfangled air conditioning stuff with refrigerant-based cooling. The way you disrupt an industry is you speak the language of the industry. If I want to sell somebody who's been sizing systems by the number of tons of ice per day they needed, then I'm going to tell them that the equivalent of your 2-ton system that needed twice 286,000 BTUs per day, we're going to take that 286,000 BTUs, which, by the way, in case you haven't figured it out, is the amount of energy it takes to melt 1 ton of ice. You take that number, 286,000, you divide by the 24 hours in a day, you get 11,900 and a little bit of change. Round that up to 12,000 BTUs in a ton. Now, why that's interesting is because melting ice is a chemical process, a physical process that doesn't change. I could melt ice in this room. I could melt it on the surface of the sun. It takes the same number of BTUs to melt the ice. The refrigerant cycle is a lot more sensitive, right? We're taking the heat from inside. We're moving it outside. So the temperature outside, that's going to be important, right? The reaction of causing condensation is about twice as energetic as the action of lowering the temperature of the air. So the amount of moisture removal I do is going to affect that, which means the level of humidity in the air is going to affect that, right? And the way things work with dry bulbs and wet bulbs, you kind of have to know what the dry bulb is to know what the level of humidity will be to measure that point. It's called a wet bulb temperature, and lots of psychrometric stuff, aka temperature, pressure, and moisture stuff is interactive, right? It's hard to know one without others, right? So I want to know the indoor dry bulb, I want to know the indoor wet bulb, and I want to know the outdoor dry bulb. And I don't know those things. I don't know how the system performs. And your HVAC guys know that. Right? They've looked at a pressure chart. When they charge these things, they have to adjust for the outdoor temperature, the indoor humidity. And by the way, I left one off, the CFM, the airflow. All of those things will change how many BTUs that system performs at, every one of them. And so that's the reason why Manual J can't give you a quote unquote tonnage, right? Because number one, there's no such thing as a ton. Number two, you change the conditions, you change the performance. A system does not give me the same number of BT. It's not a magic box. It's not a refrigerator, right? It doesn't go in everybody's house and sit at the same temperature and do the same thing in everybody's house. I'm putting part of it outside. I'm putting part of it inside. I got ductwork somewhere. I don't know. It might be in the attic. It might be in the basement. Who knows? But a system in Boston gives me a lot more BTUs than a system in Phoenix.
And it's important to think of it as a system, just like we always do on this channel. It's not an installed product. Mm-hmm. It is a system of interconnected, installed things.
Even the ones that hang on the wall. Right? There's still an outside part and an inside part, and what's happening outside and what's happening inside are going to affect that performance. So your job, Manual S, is there are sort of 2 parts to Manual S. Rule number 1, do not use AHRI data. Rule number 1, okay? Literally rule number 1, okay? Did you know the AHRI capacity? So this is, I told Corbett we were going to have a coming together moment when we talk Manual S, right? That contractor who's like, man, no way, right? They look at your load calculation, man, no way. There's no way. I need a bigger system than this. They might be right for the wrong reasons, but they still might be right. Their years of experience have taught them something, right? It's, by the way, I tell this to experts all the time, right? All the nerds in the industry. When somebody who's been doing something for 30 years tells you something, try to believe them. You might not want to believe the reason they give you, but try to believe their assertion and try to think about how might that be true, right? That has served me very well over the years. So if I have a system that doesn't perform nearly as well as I think it does, maybe it's not the load that's wrong. Maybe it's the equipment performance. And by the way, it is. When you look at AHRI rated equipment, right? I've got a little cheat sheet down here. Where did I put the stupid thing? There it is. So I've got a 3-ton units data here. It is a ton of data. It is an intimidating amount of data. And there's this little yellow box I put on there, and that little yellow box is AHRI. AHRI gives me one little data point, and the actual performance of the system is dozens of data points, right? And so AHRI is picking an outdoor temperature, an indoor temperature, an indoor humidity, and a CFM to test their systems. So they use...
And is it, out of curiosity, is it the same as the dehumidification standard that we use, which is like 80 degrees, 60%, which is so outside the
similar
realm?
So it's the same problem. It's not the same temperatures, right? So 95 degrees outdoors. Actually, I'm pretty on board on that, right? Take an average of, places where cooling is really important. 95 degrees is about in the right ballpark for a lot of the country now. Phoenix better throw that out, right? There are definitely places, and Minnesota, right? We're going to get better performance up there because it's cooler. But in general, where cooling is really important, 95 degrees kind of makes sense, right? I see where they come from on that. Good call. 80 degrees in the return. You have got to be kidding me. 80 degrees in the return is not normal conditions. Okay. 80 degrees in return is like something is wrong. Now you bring in some outside air and and get a little bit of duct leakage. The temperature may not be exactly 75, but to get it all the way up to 80, that's crazy. If you have a duct system in conditioned space, by the way, and no ventilation air, the 80 degrees is what they're saying is going to be going through your system. That means the house is 80 degrees. That's nonsense. The number that's a little harder to understand is the wet bulb, but it is more important. They use 67 degree wet bulb. 67 degrees is 50% relative humidity if it's 80 degrees. If it's 75 degrees, 60+% relative humidity if you cool that air down to 75. I don't remember what the actual number is, but it is too humid, okay? They're putting their thumb on the scale, folks, right? Because do you know what happens to the performance of the system when you give it warmer, wetter air in the return? It actually improves the system. So it's not a good thing to feed your air conditioner warm, wet air in, warm, wet air out, right? Well, warmer air in than you would have given it if you gave it cool air. But the job of an air conditioner is to move heat. There are two parts. There's an outdoor part where you get rid of heat. That's the hot part, okay? And there's the indoor part where you absorb heat. That's the cold part. Now, I don't care if you think it's compression or magic that causes that heat to move. The cold part's job is to absorb heat, right? You give it warmer air, what's it going to do? Is it going to be better at its job or worse at its job? It's going to be better at its job. It's going to be easier to pull that heat in and send it outside to the magic part outside that gets rid of the heat. So when we say it's going to be 80 degrees in the return and a 67 degree wet bulb, warm wet air tells me that the capacity of this system is 33,600 BTUs. It's a 3-ton system. By the way, that's not already 36,000. It's 33,600. Here's the thing. If I look up what the performance of this system is when it's 95 degrees outside, I'll give them that one. 75 degrees in the return. And a 63 degree wet bulb. The performance of this system turns into 31,160 BTUs.
Just a little over 2.5 tons.
Just barely, right? We think of a 3-ton unit as being 36,000 BTUs. Take it out of the laboratory, introduce it to the real world, and all of a sudden it is way closer to 2.5 than it is to 3. And if I have a homeowner who wants, homeowners, don't set your thermostat at 70 degrees. You're setting it below the outdoor dew point. It's a terrible idea. If you're in Denver or someplace, I guess you can get away with it. It's still not very efficient, right? Remember, colder air in the return, harder to do its job, right? So the colder you make it, the harder it's going to work. If I drop this thing down to 70 degrees and a 50% relative humidity, right? That means it's going to have a 59 degree wet bulb, and that's going to be below 30,000 BTUs. By the way, that's not every 3-ton system. That's this 3-ton system, this coil, this condenser under these conditions, right? And so now my 3-ton unit has less than 30,000 BTUs. That's why rule number 1, don't use the AHRI data, right? It's good for doing apples to apples comparisons, right? I want to know how efficient this is compared to how efficient that is. Well, you got to test them under the same conditions. They got to pick something. What they picked was a little silly. But okay, that's what they picked. So if I'm using it to see how efficient is this compared to how efficient is that, not bad. If I'm using it to see if this is the right piece of equipment for my house, terrible, right? Because the other thing AHRI data doesn't do is it doesn't tell me how good the system is at removing moisture. It does not give me latent capacity. It just gives me a total, right? How much moisture removal is doing? Anybody's guess until you go and look it up.
And so this chart and that data comes from the they call it the manufacturer's OEM extended data. Is that what it essentially?
That is what they call it in the book. Yes.
And where do you find that?
Yeah. So you got to find that. So for once upon a time, you used to just Google that condenser model number, and you could go and find some distributor that didn't put a password on it, and you can go find it. These days, mostly they don't publish the tables anymore. They have calculators, right? And it's the dealer site that you've got to log into, right? The homeowner facing site isn't going to do it, right? If I go to train.com, I'm going to be sold an air conditioner and a heat pump. Man, of course they are, right? I want to know, as a homeowner, I don't want to know how to use a technical performance data like this. It's scary. But they have something called Comfort Site, and it's for their dealers, and they will take third-party designers, and you usually have to work with the local distributor to get yourself a login to these tools, right? But if you call them up and say, hey, I'm trying to sell your equipment locally, I'm trying to help out your dealers, they'll be like, here's your tool, right? They have a login for you. And then, Carrier is HVAC Partners, and Lennox is Lennox Pros, and the list goes on, right? And so you go into that website, and you always need a password. You get access to this information, and then you look up what the system will do in your conditions. They don't have the charts anymore, they're calculators. Because this thing only tells me 85, 95, and 105, right? 70, 75, 80. You can get in between those things. And that, by the way, is where the manual S gets squirrely. The manual S does a lot of things called interpolations, right? Interpolations. So you've probably heard the word extrapolate, right? Extrapolate is when you see a pattern and you continue it on even though you don't have data. That's an extrapolation. X meaning it leaves the data set. Interpolation means you're playing inside the lines. So I know I'm here and I know I'm here and I know I'm halfway between, so I can figure out where halfway between is on that. The thing is when you actually figure out how much interpolation you need to do, you have an outdoor temperature, an indoor humidity, and a CFM, that turns into 32 data points. It's a good thing they have the calculators, because doing it by hand or even doing it with the speed sheets from ACCA can be a pain in the butt. And so you give it the actual temperature outside and the actual temperature inside and the actual humidity level. I'm usually using a 50% coincidental, whatever that happens to be, which also matches up the data points on this thing that I have in front of me. It's 70, 59, 75, 63, 80, 67. Those are all 50% relative humidity. So if I use that information and I hit, tell me what it does, right? I hit calculate, it will give me a sensible and a latent. Okay. It will give me both. So it probably actually won't give you those two numbers. What it will probably do is it'll give you a total and a sensible, or a total and a sensible heat ratio. That's really easy. It's a percentage. If it's 0.8, 80% of your total is sensible, 20% is latent, right? The reason they leave you to do the math is stupid. It's legacy stuff. They used to have to print this on paper. The chart had to fit on the paper. All right. So they couldn't publish every number. So they published what fit and then let you figure out the rest. They have calculators online. There's a couple of manufacturers who stopped making me do this, and I love them for it. Like, show me the numbers, for goodness sakes. You have a calculator that's doing all these interpolations. I think you can handle some subtraction. But once I have those two data points, now I know what the thing actually does. All of that is rule number one. Rule number two is all of the rules for sizing the system, not oversizing it, making sure you have enough, et cetera, et cetera. And we can talk about those, but it all bases off of making sure you're using the real data, right? And once you find out what the actual performance is, now you can say, okay, does this match my load, right? Is this going to remove the moisture I needed to remove? Is this going to satisfy the temperature too quickly? No, yeah, no. And if not, okay, we have a match, we have a system, but I don't know until I know how the system is going to perform. And I don't know that until I look it up under real world conditions.
You guys, this is going to be one of the longest videos we've ever put out, even if we stop it right here, which we're going to do right now. So what I want you to do is, if you want to learn more from Alex and his gigantic brain, tune into part 2, which is going to be released separately. I'm linking it on screen right now. It's also in the description below. But please do comment if you have things to add, questions as well. Post down there. We address those personally. I'm going to drag Alex over to deal with some of those too. Like and subscribe. Tune in next time.